Hi, I'm Janine Cody, Director of the Chromosome 18 Clinical Research Center, and I'm often asked about why any two individuals with the same chromosome 18 condition are so different. And so I wanted to share a little bit about what we know and how we think about this problem. So as you know, there are 5 groups of chromosome 18 conditions. But within each group, there's huge genetic variation from one person to the next. So every single person with an 18q deletion, a deletion of the long arm of chromosome 18, has a slightly different deletion or region of the chromosome that's missing. And for example, many people or everyone with an 18q duplication has a different region of duplication. Same goes for the P-arm or ring, or there's huge genetic variability between any two people, even though they're in the same group of chromosome 18 conditions. And so how are we ever going to understand this, and how do we think about the process? So what we need to do is take a gene-by-gene approach and start to understand the role of each of the genes, of each of the 263 genes on chromosome 18. And this is a pretty big process, but we've been working on it for 30 years now, and we've learned a few things. We've learned, for example, that the vast majority of the genes are really just bystanders. They don't care whether there's 1 copy or 2 copies or 3 or 4, they do their function just fine, doesn't mess up anything. There are just a few, those rare ones, that are the culprits. And that's what we need to learn more about. But first, we need to figure out which are those culprits. And we've made a lot of progress in that regard. So the way we talk about it is categorizing the genes into 2 big groups. The bystanders we call dosage insensitive genes. They're not sensitive to the gene dose, the number of copies, whether it's 1, 2, 3, or 4. And they do their thing without messing up anything within the body when there's this abnormal gene dosage. Then there are the dosage sensitive genes, which do cause a problem. But even within the group of dosage-sensitive genes, there's a lot of variability with what percent of the people those genes cause a problem in, because it's not always, or not usually, 100%. In fact, in dosage-sensitive genes, there are 15 of the 263 on chromosome 18 that we consider causal. And if you have a deletion of one of those genes, only more than 50% of the people are affected by that, or greater than 50%. So it's still not everybody for most of those. And 9 of those that we call dosage sensitive cause a problem in less than 50% of the people who have a deletion of that gene. So there's a lot of variability even among the dosage-sensitive genes. And as well, the dosage-insensitive genes. And I wanted to talk a little bit about why sometimes in rare cases the dosage-insensitive genes can actually cause a problem for one person or a very small group of people. So I wanted to talk about how we conceptualize all this. How does this work? How do we envision this happening? And why are these different? How can this be? So here's my little diagram on how I think about this. And so here we have Tom, and he has 2 copies of gene A. And so the height of the bar indicates the activity of that gene. So he has 2 copies of gene A, so that's normal. They each are creating the optimal amount, the typical amount of gene product. So the total between these 2 are the total of gene activity for gene A that Tom has. And so we'll have Tom here in every slide just to show you what typical is. In Tom's case, all is well, because this is how we define normal in this instance. Now, for disease gene A, now we have 3 people, Tom, Dick, and Harry. Tom, of course, has 2 copies of this gene, and all is well. But for disease gene A, if your any one individual's total level of gene activity falls below this line within the bracket, you have disease caused by gene A. If you're above that, you're fine. So in this case, Dick, he has 2 copies of this gene A. One works perfectly fine. The other one, the pink one, copy 2, has a mutation. It is not working well. So Dick would have this disease. Harry has only 1 copy of the gene. Copy 2, the pink one, is completely missing. It's deleted. He has 1 perfectly normal copy, but it isn't sufficient. So in this case, both Dick and Harry have disease A. And so this would be a dosage-sensitive causal gene. And this is how we think about Pitt-Hopkins syndrome and the TCF4 gene. You really have to have every bit of more than one copy working in order to not have Pitt-Hopkins syndrome. But it's the only gene like this on chromosome 18. So this is really the rare example when the bar sort of to not have the condition is so high like it is in this example. Here we have another gene, so disease gene B, and this is what we see more often. Again, Tom, he has 2 copies. Dick, Harry, and Bill, they each have a deletion of 1 copy, the pink copy. It's gone. But interestingly, and this is probably what we have most of the time, Dick has perfectly average copy, but Harry and Bill, they have variants in their existing copy, or mutation, however you want to talk about it, and it makes a little less than normal. So in this case, for disease gene B, the amount you need to not have disease is lower than in the last example. And so Dick and Harry have sufficient amount. They do not have this characteristic or disease, but Bill, on the other hand, he does. In this case, 3 people have a deletion of this gene, but only 1 of them has the actual disease. So 1 out of 3 with this gene deletion have disease. So this would be low penetrance. So this is how we think about the low penetrance genes that we've categorized. People have a variant on their normal copy that maybe makes them susceptible. And of course, this is genetic, so anything could happen. So it could be a mutation on another gene that causes this gene to not be fully active. So that's how we think about dosage-sensitive genes, the causal ones that are more than 50% of the people with a deletion of that gene have the disease, and the low penetrance because of variability in the existing copy is really, in both cases, makes the difference between whether or not someone has the disease or doesn't, or has the characteristic or doesn't. And here's another case, same disease gene B, but in this case, maybe I should have given them different names, but in this case, Dick and Harry have 2 different instances. So Dick has both copies of the gene. Unfortunately, one of them, the pink one, copy number 2, has a mutation, and it hardly makes any protein at all. But he has a perfectly good copy. The blue number 1 copy is perfectly normal, makes the right amount. Harry, on the other hand, he has a deletion, but again, he has a fully functional copy. It makes enough of the gene product, and so neither of these individuals have disease gene B. So what we would do is what we call in genetics, Dick would have be a carrier for a recessive condition. And we're all thought to be carriers for numerous recessive conditions. one copy is there and fully intact, and the other copy has a mutation that makes it non-functional or barely functional, but is still above the disease threshold, so you have no idea you're a carrier. Dick has no idea he's a carrier for this condition. And Harry, on the other hand, just has a deletion, which is almost like being a carrier, and so he doesn't have the disease either. So this would be what we would call a dosage insensitive gene. Someone with the deletion does not have this condition. They're really just the same. A gene deletion carrier is the same as a mutation carrier. In either case, they don't have the condition. This would be a dosage insensitive gene. But what happens if Harry has a deletion and he only has one copy? The pink one's gone entirely, but his blue copy has a mutation. Then he has the condition. So, what are the chances that any one person has a deletion of a gene and one of the rare mutations in that gene? So, this person, what we say is he has a revealed recessive. He has a recessive mutation in his existing gene. So, he in fact does have this disease gene, even though we called it dosage insensitive. But this is going to be so rare when someone has a mutation in the existing copy, their one single remaining copy. So the reason we keep track of this is because I get phone calls and emails from families and their doctors saying, someone with 18p minus has this unusual symptom. And is it related to 18p minus? And so we look in the database, no one with 18p minus has this symptom, so but we don't want to say it's totally unrelated to having 18p minus, because then what we do is look at the genes involved that we call dosage insensitive and see if any of those are associated with a recessive condition for which this is a symptom. And sometimes that's really important because the symptom could be the result of any of 4 different conditions. And if we know that there's a possibility it's associated with a recessive condition gene on 18p in this case, then we can set them down the path to investigating that specific disease that symptom is associated with. So these can have relevance, but in very, very rare cases. But that's why we keep track of this, and that's why we've created this category of dosage insensitive genes that we call conditional, because of this potential for revealed recessive. And then there are the ones that we think about as truly dosage insensitive. In this case, this would be like disease gene C. The bar for having the disease or a disease caused by this is so low that even when Harry and Bill have mutations in their single remaining copy, they don't have the disease. And this is the vast majority of genes on chromosome 18. And most of the time, it really just doesn't matter if you have 1 copy or 2 copies. And if your 1 copy has a variant that makes it a little sub-average, has no effect. And this is the majority of genes, and this is kind of how we conceptualize this issue. So these are those, like I said, with no effect, and that's 139 genes out of the 263 that we've categorized in this way. But again, this is really just the state of the science, and so it does evolve, it does change, and if I do this same talk in 2 years, these numbers might change slightly, the number of genes. So it's a work in progress. We're actively working on, but we've made a lot of progress to get this far and to start to categorize the specific genes and learn which ones are the causative ones. And from there, now we can learn about upregulating or downregulating those that are dosage sensitive, which is another set of talks and a whole lot of research that we still need to do. And if you have any questions, as always, I love hearing your questions. Please email us at chromosome18@uthscsa.edu. Your questions will be helpful for a lot of reasons. One, you'll get an answer. Hopefully I'll be able to answer or tell you at least what we know so far. But also your questions usually mean somebody else has the same question. And so that's usually how I decide about, oh, I better do a video or write an article about that topic. So I appreciate your questions very much. Our website is here for the Chromosome 18 Clinical Research Center. And I look forward to meeting every single one of you in person one day at our conference. See you soon.